Welcome to day 25 of calculus. This is where we bring everything we've been learning together and start making some really pretty graphs by hand. First, let's remember a couple tools that will be useful for us, and those are polynomial long division and synthetic division. So if I ever asked you to factor a polynomial, we have methods like grouping and just figuring out how to factor by hand. But if I tell you that something is a factor, and I tell you if I give you a factor that isn't a linear term like x plus or minus a constant, you need to use polynomial long division. And you do that by writing out x squared plus 1, and then underneath it you take and write the polynomial you're dividing into. And now you need to remember one phrase, and that's leading over leading. Leading over leading. So you take x to the fourth over x squared, and you end up with x squared, and you write that over the x squared term, and now you multiply by both of those terms, and you get x to the fourth plus x squared. And remember, I'm writing these all underneath the term, so x squared times 1 is x squared. Now you subtract, and you end up with 2x cubed minus 8x squared, and now your new leading term is 2x cubed. This leading term stays the same. So now we have 2x cubed over x squared. That's going to be 2x. So we have plus 2x. And now we do the same thing again. Now we multiply everything by 2x. So we end up with 2x cubed plus 2x, because that's 2x times 1. And you subtract, put the parentheses around. So now you have negative 8x squared. These cancel, and then you drop the negative 8, minus 8 down. So now what do you have for a leading term? Your new leading term is negative 8x squared. So you have negative 8x squared over x squared, same leading term here. You ended up with negative 8. The minus 8, now you multiply, you end up with negative 8 squared minus 8, because negative 8 times 1 is that, and then you end up with 0. You should end up with 0 because we know this is a factor. If something is a factor, the remainder is going to be 0. So what does that tell us? It tells us that this polynomial right here turns into x squared plus 1, we know that's a factor, times our new quotient x squared plus 2x minus 8. So we're to here now. Polynomial long division gave us this term, but we're not done because we need to factor that term, and that's just a quadratic, and it's going to be x plus 4 times x minus 2. So now we have fully factored the original polynomial. The key term to remember is leading over leading. But if I gave you a similar question, but I gave you a linear factor, you can use polynomial long division. To do that, what number makes this 0? Negative 3 makes that 0. So you take negative 3, you make a line like this, and then you take the coefficients of what you're dividing into, and that's going to be 1, negative 9, negative 3, negative 36. The first thing, and those are the coefficients of this polynomial in order. The first thing you do is you drop the first term, and now you're going to multiply by the negative 3, and that's going to be 1 times negative 3. It's going to be negative 3. And now you add, you get negative 4. And now you do the same thing. Multiply by negative 3 to get 12. Add these together to get 3. Multiply by negative 3 to get negative 9. Add these together to get negative 12. Multiply by negative 3 to get 36. And now add them and get 0. Again, your remainder should be 0. The wonderful thing is that now we knew that x plus 3 is a factor. The nice thing about polynomial synthetic division is that these terms right here are the coefficients of what remains. So that means you have the constant, the x squared, and the x cubed. So that means you have 1x cubed. I can only almost write that 1x cubed minus 4x squared plus 3x minus 12. There's the 1, there's the negative 4, there's the 3, and there's the negative 12. We're not quite done. We need to keep factoring. And now you're going to try to do factoring by grouping, which we can do. The x plus 3 stays there. And what can we factor out of the first two terms? We can factor out an x squared. So you get x squared times x minus 4. And then let's factor out a 3 here. And we end up with x minus 4. So that means this factors into the x plus 3 stays. But now you have x squared plus 3. There's the x squared and the 3. And you're left with x minus 4. So now we have fully factored that polynomial. So those are two factoring methods that you need to remember: polynomial long division and synthetic division. We will practice it extensively in class. So now we're going to answer this question right here. It says graph accurately each of the following. So we're going to graph this function, find intercepts, find many things, maximums, minimums, and points of inflection. Do this piece by piece. Intercepts, find all intercepts. Let's do that first. Intercepts are where it crosses the x-axis. So that's when the original function is equal to 0. So we take the original function, x cubed plus 3x squared minus 4x minus 12, and we set it equal to 0. We are finding the intercept. We have a cubic, and we aren't given any factors, so let's try grouping. We can factor out an x squared and get x plus 3. We can factor out a negative 4 here and get x plus 3, and that equals 0. That's our goal because now we have x plus 3 in both cases. So now we can factor this into x squared minus 4 times x plus 3 equals 0. And then this is the difference of squares, so it's going to be x plus 2 times x minus 2, and the x plus 3 still stays there, equals 0. So now I know x is equal to negative 2, 2, or negative 3. So we have three intercepts, negative 2, 0, 2, 0, and negative 3, 0. So we take those 3 points. Here are our x-intercepts right there. We graph them over here. They're going to be at negative 2, 0, 2, 0, and negative 3, 0. So let's go up. We're checking off intercepts. And we're doing these exactly, by the way. So what about all maximum and minimum values? So for maxes and min, so maximum and minimum values, we need to look at the first derivative. So let's look at the first derivative. F of x is a polynomial, so f prime can be found using the shortcut. Drop the 3 to the front, so 3x squared plus now 6x minus 4. So that's our first derivative. And since we want to find maxes and mins, we want to know where the derivative changes from negative to positive or positive to negative. So we want to know when does the derivative 3x squared plus 6x minus 4 equals 0. We want to know when that equals 0. This is where you hope it's nicely factorable. Unfortunately, this quadratic is not nicely factorable, so you need to use the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You have to remember that. This thing here is called the discriminant, so find that first. And in this case, here's our a value right there, here's our b value, and there's our c value of negative 4. So do the discriminant first. That's going to be b squared minus 4ac. So that's going to be 6 squared minus 4 times 3 times negative 4. C is negative. That's really important there. So that turns into 84. So our discriminant is 84. So then you end up with x is equal to negative b. So it's going to be negative 6 plus or minus the square root of 84 all over 2a. So that's going to be 2 times 3 is 6. So then you have two answers when you add them and when you subtract them. And to get a decimal, you can simplify it a little bit. You end up with negative 6 plus or minus 2 root 21. You can factor out the 4. It turns into 2 if you want to over 6. The decimal equivalents to these, if you do them out, you're looking for the decimal equivalent of negative 6 plus root 84 over 6. That's our first point. And then the y value, you need to use your calculator for that, and then negative 6 minus the square root of 84 over 6. Now you can change these to decimals if you want to. If you do the top one right here, this right here, the decimal form is 0.528. It goes on, but you can go stop after 3. And then the bottom one right here in decimal form is negative 2.528. Now these also need to be accompanied by the y values. You then take those decimals, hopefully you've saved them using the store function, and plug them into the original equation. Remember, you have to plug into the original equation to get y values. And if you plug those into the original equation to get y values, you end up with negative 13.13, goes on a little bit too, and 1.128. So I know this process was a little harder. It would have been nice if this right here had been nicely factorable, but it's not. You have to use the quadratic formula, and to get these decimals you need to use a calculator. You're going to have to use a calculator. So now we know the derivative is 0 at these x values, but we don't know if these are maxes or mins. These are right now potentially, is it a max or a min? And is this a max or a min? We don't know. Could be either one, or we're going to figure out if it's a max or a min at each of those points by using the second derivative. But let's plot them first. If we plot them, So we're at 0.5 and negative 13. So we're like 0.5, negative 13 is right about like here. So that's this first point, I just plotted it. And then you're at negative 2.5 and it's 1.1. So negative, so right about here. So I just plotted those points. We don't know if they're mins or maxes. We can suspect, but we're not sure. So to find out if it's a min or a max, we need to look at the second derivative, and look at concavity. So here was our first derivative. Our first derivative, I'm going to write it again, was 3x squared plus 6x minus 4. To determine concavity, we need to do this, look at the second derivative, so f double prime of x. So it's going to be 6x plus 6. And then what we're going to do is we're going to take our values that we found here, these two values, the 0.528 and the negative 2.528. So we're going to do f double prime of 0.528, plug that into the second derivative. And when you plug that into here, you know that that's going to be greater than 0. 6 times that number, you know, it's 6 times that number plus 6 is definitely going to be greater than 0. And we know that f double prime, if we plug in negative 2.528, we're plugging this number in to there. If you plug that in, it's going to be less than 0. So what does that mean? It means that the concavity, if it's greater than 0, it's going to be concave up, and less than 0 means concave down. So we know the concavity is concave up right there, so it's a U shape, so this is going to be a min, and if it's concave, so this was concave up at that x value, this will be concave down, so this is going to be a max, and that kind of matches what we have right up there. So we know it changes concavity, you know, it is concave up and concave down. So we found the maxes and mins. We know that this is going to be a max right here, and we know that this is going to be a min right here. The last thing we need to find is the point of inflection. The point of inflection, that's where the graph changes concavity. So you look at the second derivative, which is 6x plus 6. So we have 6x plus 6, and where does that change from positive to negative? Well, you set it equal to 0. Factor out the 6 plus 1 is equal to 0, so x equals negative 1. And then we know that when x is equal to negative 1, the second derivative of x is 0. So we need to know what happens to the left and what happens to the right. So you plug in a number to the left of negative 1, and that, let's say, would be negative 2. Plug that in here, what do you get? 6 times negative 2 plus 6, so we're doing f double prime of negative 2, and that's going to be negative 6. So it's going to be concave down to the left of negative 1. And then what's f double prime? What's to the right of negative 1? 0. So it's going to be 6 times 0 plus 6 is 6. So it's going to be concave up. So we know when it crosses negative 1, so right here, when it crosses negative 1, you know that it's going to be concave down to the left on this side, so concave down over here, and then once it crosses here, it'll be concave up. So we can start drawing this and see what happens. So concave down, it's concave down to here, and then it's going to change to concave up. And that's a little straighter than it should be, so I'll zoom in here to make it a little more curved like this. So we know it changes concavity when x is equal to negative 1 right there. So I'll draw this a little bit more carefully. If we want to know exactly where that point is, what we need to do is take negative 1, our negative 1 right here, and plug it into the original function, which is x cubed plus 3x squared minus 4x minus 12. So f of negative 1, if we plug in f of negative 1, you end up with negative 6. So that point of inflection should be at negative 6, which we were pretty close to. So if we actually make it hit negative 6, it'd be negative 1, negative 6. It's going to be concave down to here, and then change to concave up. So we have concavity being concave down. So we have concave down from here to here, and then it changes to concave up from here to here. Just like that. So we now have an accurate graph of what's going on. We could check the first derivative as well. And what that would tell us is that it is going to be increasing all the way to here, and then it'll be increasing here, and then in between it'll be decreasing. The last thing it asks you to do here is state the end behaviors in limit notation. So the end behaviors are the limit as x goes to infinity of f of x. So let's look at this function right here. As x gets huge, what happens to this? Well, x cubed is the only one that's going to matter. Everything else is really small. So if x is positive and really big, this whole thing is going to go to infinity as well. And does that match what's going on here? Yeah, it's going up. What about the limit as x goes to negative infinity of f of x? Well, it's the same f of x. It's the same f of x, and so x cubed is the only one that's going to matter. But when you cube a negative, the whole thing will be negative. So this goes to negative infinity. So is this going up? It is, and then as x goes to negative infinity, this goes down. So the end behaviors match. The end behaviors match. So objectively, this is a lot to put together, but do it piece by piece. Don't try to do it all at once. Do the intercepts, then the maxes and mins, the point of inflection. Use your highlighter. Use your calculator when necessary. Yeah, I know it's annoying that was not nicely factorable, but sometimes you're going to have to use the quadratic equation to find solutions.